I'm so sorry that we didn't have enough time to get to everything in class. It's a real bummer. But maybe it's better this way, right? We get to finish in this nice, warm, friendly environment. You'll have something permanent. It's real chill and relaxed, right? We're not rushed. Casual clothes. Chocolate milkshake. This is how education is supposed to be. Ooh, do we have any Rice Krispie treats? So when we left off in class, we just finished talking about the regression line. The line of best fit, the best summary of our data that we can possibly get, where the total sum of the squares of the residuals is as small as it can possibly be. And we saw how that can give us this visual picture of the pattern of our data. And it allows us to get predictions of it too, with extrapolation, going beyond our data, or interpolation, going between data points and seeing what we can predict about values there. It gives us this idea of not only what does our data look like, where is it going, what's the pattern, what's the form, what's the strength, but it also gives us this ability to predict what could happen, what should happen, if we were to get another instance of the explanatory variable. Where I want to go before we get to inferences and whatnot is I actually want to look at a couple other relevant statistics that we often consider and look at and are very interested in when it comes to correlation. So let's have a look. Number 5. Another way to measure correlation is with the correlation coefficient. The correlation coefficient is a number that we can calculate once we have the regression line. Its calculation comes from knowing the regression line, but we're not going to look at the formula here. Instead, we're going to rely on technology to give it to us, and I just want to talk about what it means and how we're going to interpret it here. So here are the facts. First of all, the correlation coefficient uses the letter R, lowercase r. That's the symbol that we use for the correlation coefficient. I don't know why. Correlation? That's my best guess. I got nothing. Now, the value of R is always between -1 and 1. Always those values. It could be 1 or -1, but it has to be in between those. You never get a correlation coefficient of like 2. What do those values mean? Well, first of all, positive values of R mean that there's a positive correlation between the variables. As the explanatory variable gets bigger, the response variable also gets bigger. As one goes up, so does the other. A positive value of R means that. Positive correlation. Negative values of R means that there's a negative correlation between the variables. As the explanatory variable gets bigger, the response variable gets smaller. As one goes up, the other one goes down. There's a negative correlation. What do the numbers mean? Well, the actual number of R is giving us an indication of how much correlation there is. How correlated are these two variables? How connected are they to each other? If you've got values that are close to 0, that means that there's very little correlation between the variables. Potentially nothing. If R is between 0.3 and 0.7, that also goes for -0.3 and -0.7, then there's a moderate correlation between the variables. There's something to say there. There seems to actually be some kind of connection. And if R is bigger than 0.7 or less than -0.7, then there's a strong correlation between the variables. There's a very strong connection. Knowing something about the explanatory variable tells you a lot about the response variable. You're going to be really good at predicting its values with your regression line. In fact, if R is equal to 1, that would mean that all of your data points are on the regression line. That your line of best fit just cleanly goes straight through all of the points, that they are linear. Granted, that's almost never going to happen, but if you get something that's very close to 1, then that means that everything is going to be very, very close to that line. Or if you've got something close to -1, then same deal, everything's very close to that regression line, it's just that your regression line has a negative slope. The sign, positive or negative, of our correlation coefficient r is always going to agree with the sign of the slope of the regression line. They're both positive or they're both negative. For my section 6 class at 2 o'clock, for your data, the correlation coefficient was 0.4194. That actually is moderate correlation. That there is kinda something there to say. So that is actually kind of surprising for me. Hey, maybe I'll actually get a significant p-value. Who knows? Let's not get our hopes up. Section 4, if you're curious, your correlation coefficient is r equals 0.2845, which is a bit less impressive. Not even moderate correlation. What a bummer. The correlation coefficient is a really powerful tool. It's a great measurement of how strong the correlation is. But there's actually one more statistic that we often consider when we're talking about correlation and how strong that correlation is, called the R-squared statistic. Oh, that was a phenomenal idea. I'm gonna do that again. So, number 6. One more statistic we often use is the coefficient of determination, capital R squared. Now, I'll admit, I got thrown here as a student because little r was the correlation coefficient, and now this capital R squared is the coefficient of determination, but they actually are like the same r. It's I don't know why they changed it to a capital R here all of a sudden in most texts that I see, but yeah, if you take the correlation coefficient and square it, you've got the coefficient of determination. But interestingly, they have kind of totally different meanings and purposes here, so let's talk about this one. Here is the idea of the coefficient of determination. Here's what it's doing for us. First, we're going to look at the average value of the response variable, y bar. Right, remember, both of my variables here are quantitative, right? I've got x bar would be the mean of my explanatory variable, y bar would be the mean of my response variable, and I'm going to look at that for a moment, right? I've got all these different values of the response variable. Hey, let's look at all of them together. Forget about lines for a moment, just look at the numbers that I get for the response variable. What is the average outcome for them? Okay, well, what if our regression line was just a horizontal line at that value? Like, here's some those made-up points that I had earlier, and here's, the regression line that we originally came up with in blue, and here's the purple line, is this horizontal line that's just the average value that we get, around like 8.5, I think, for all of the y values for these red points. Well, that's the average. What if I just had a horizontal line there? What if that was my regression line? How bad could it be, right? Well, for any line that we're using to try to summarize our data here, right, I can think about that sum of the squared residuals and sort of test how good the line is based on how big that sum of the squared residuals is. Our regression line was the best it could be. This horizontal line at the mean is the worst it can be. You can't do worse than this horizontal line. It's as bad as it gets. So, that being said, how much of the sum of the squares are we going to save by using the regression line instead? If the horizontal line gives me the worst possible sum of squares, and the regression line gives me the best possible sum of squares, then what's the difference between those two? How much do I gain? How much better is the regression line than just the mean, right? If I just compared each of my y values to just the average y value, how much worse is that from comparing their y values to this regression line? And the idea that we're getting at here is, if there's no correlation between these two things, then just looking at the mean is a fine summary, right? If there's no actual pattern or connection between the explanatory variable and the response variable, then I don't gain anything by having a regression line. The regression line doesn't summarize the data any better than just having the mean. So that's what we want to look at and see, okay, well, how much worse is it? How much more do we gain, or how much better is the summarization of the data using the regression line? I'll look then at this sum of the squared residuals that I get from just using that horizontal line at y bar, and comparing that to the sum of the squared residuals that I get from using the regression line. If you look at, here's my, oh, that's a pen. I want a pointer. Laser? Oh, yeah, there we go. Right, if I look at, like, you know, this point down here at 0, 1, from the regression line, well, my regression line gets pretty close to, like, 3 here, I'd say. And so the squared residual, right, my residual here is about 3, -3. Squared is 9. But if I was comparing it to the mean value instead, okay, well, that's up here at, like, 8.5. Alright, so now I've got 8.5 is -8.5 is my residual. I'd have to square that and then add all of those up. Okay, well, some of these points actually do a little bit better from the horizontal line, but not all of them, right? Some of these up here are going to be way better approximated by the regression line. So the big question that we're looking at here is just, okay, well, let me take the sum of the squared residuals from each of these points when I just look at how their y values differ from the average y value. And then I'll look at how much different it is from taking those sum of the squared residuals from the regression line. How much better is it? And here's the big question, is that a lot? I look at this value, I get this value of the difference between the two. I know that the horizontal line, the average value, is the worst I can do. The regression line is the best I can do. I'm going to get some value here. I'm going to get some amount. But I don't know if it's a lot. I need to compare it. I need to do a comparison. And what I'm going to compare it to is actually the original sum of squares from the average value. In other words, I'm going to look at the worst possible sum of squared residuals that I could possibly get, look at how much I save by using the regression line instead, and then comparing that to the original sum of squares, right? It's like I'm saying, hey, what percent of that total worst amount of squared residuals goes away by using the regression line? Looking back at our points from before, you might recall that with our regression line, the total sum of squared errors ended up being 28.7572. That's the best we can get. Now, if instead you go by the average value and you look at the sum of squared errors, the sum of squared residuals from each point to the average value, well, what's the sum of squared residuals then? Turns out it's a whopping 163.75. Just a smidge different, really. The difference between those then is 134.9928. Is that a lot? Well, when you compare it to the original 163.75, you get that it's 82.44% of that. Yeah, that's a lot, right? That means that out of all of this total, residual distance that we had, right, all of the differences between my points and the average y value, 82.44% of that went away when I used a regression line instead. Now, because this is giving us like a percent in a way, right? Like what percent of that sum of squared error is going away because of the regression line, that means that the r squared value is always going to be between 0 and 1. That's how percentages work. But here's a really useful way that I find to think about it and interpret it. I like to say it like this. You're going to see different values in your response variable. That's just how it is, right? That the chances of each of you getting exactly the same distance from the donkey's tail spot, infinitesimally small, right? There's gonna be different values. The value of r squared is telling you what percent of those differences is because of the explanatory variable. You've got some differences in the outputs in your response variable. That's just gonna be that way. But how much of those differences are just because that's how it goes and that's the way the world works, and what percent of those is because the explanatory variable is changing? r squared is giving us a value that represents that. R squared might not be a value that we end up using as part of like a test of inference, but it is an interesting value on its own that connects our explanatory variable and response variable and gives us a picture of how much information is the explanatory variable really giving me. By the way, there is an r squared variable with a nova too. We just didn't talk about it, but it means exactly the same kind of thing there. I'm going to see different values in the means between the different groups, right? I'm going to get different means in those groups. That's just how it goes. What percent of the differences between those means is because of the difference in the explanatory variable, that categorical explanatory variable that's putting things in groups. What percent of the change in my response variable is because they're in different groups. Section 6, my 2 o'clock class, your r squared variable ended up being 0.1759, which is not that high. It's not. Yeah, now that I look at it in my head, like the little r was kind of nice, but now that I'm looking at this one, it's not that impressive, actually. It's a little disappointing. Section 4, your r squared variable is 0.0809. There's all kinds of differences in the response variable and your accuracy, but only about 8% of those differences can be explained by the number of spins. One last thing I want to mention here before we move on to inferences is that we can sometimes improve the correlation that we're seeing by grouping the data using some other categorical variable. Maybe I've got a scatter plot and I've got the, information about how my two variables are correlated, but it's possible that if I were to group those data points even further with some categorical variable, that my correlation coefficient or my r squared, my coefficient of determination, that those might get better if there's some other variable that might be impacting them. For example, suppose that I'm looking at this scatter plot, this information here, which looks at whether a person's height is correlated with how long they can hold their breath. Now there does seem to be some correlation here, right? There's definitely a pattern that's going, but there also seems to be some pretty strong separation between what it looks like two majorly different groups. And whenever I look at and see something like that, I start thinking about, okay, well, what's the difference between these points and these points? Now, this is all fictional data, but it's made to prove a point. So in this case, I look at, okay, well, what are some of the other things that might impact how long one is able to hold their breath, right? What are the other variables that might be relevant? Like, would it be relevant to split it up into like men and women? Well, maybe. Men generally have a larger lung capacity, so maybe they'd be able to hold their breath longer. With everybody together, the R value here, my correlation coefficient, is 0.616. It's moderate, right? It's not 0.7, so it's not strong. There's definitely a pattern. I see the correlation. But if I start grouping them by gender, right? If I start grouping them by biological sex, then, oh yeah, it looks like those might actually be grouped together. And if I separate them further, right, and look at the pieces that are like just, male versus just female, those R values just shoot right up, right? Looking at the data as a whole, yeah, I could see some correlation, but there's an even stronger correlation if I just look at them one group at a time. I might be able to glean even more correlation. And hey, the more information, the better, right? The stronger the correlation, the better I'm going to be at predicting the future. The better I'm going to be at doing that extrapolation and interpolation. So those are all the major pieces I want to talk about in regards to exploring the data. So let's actually have that conversation now about drawing inferences on the data. How do we actually come to any sense of statistical significance around correlation? Well, to answer that, let's answer the three big questions that we answer in every scenario in this scenario. Let's draw some inferences. are three big questions, starting with, how do we simulate the null hypothesis? And keep in mind, this is really the question of, what does it mean to get what we got by random chance? What does it mean to get what we got by random chance? Well, anytime we're talking about comparisons, anytime we're comparing two groups or two variables, our answer to that question of what does it mean to get what we got by luck has really always come back to just the random assignment. When we talked about comparing two groups and their proportions or their means, ultimately our randomness, our luck, was coming in through the statement, well, you were going to get what you got no matter what. It didn't really matter what group you were in. That's just who you are. That's just what happens, right? If it's you close your eyes and you have to guess when 60 seconds has passed, it doesn't matter what group you're in. It doesn't matter if the background music has lyrics or not. You were going to get what you got no matter what. When it came to trying to remember as many words as you could, it didn't matter whether they were pictures or written words. You were just gonna get what you got no matter what. If you remembered 14 words, you're just a 14 words kind of person. That's just who you are. The fact that you were in one of those groups, random chance. So when we simulated randomness, when we simulated the null hypothesis, we really ended up just simulating random assignment again, right? Getting what we got by luck is that you were gonna get what you got no matter what. The reason I got my statistic is because you just happened to end up in the group that you did. And the same thing is being said here. If these two variables are not correlated, if they have nothing to do with each other, if the number of spins has no effect on how accurate you are going to put the tail on the donkey, then you were just going to get what you got no matter what. You were either going to be close or not. If you were within 20 pixels, then you're just a 20 pixels kind of person. And if you missed the donkey entirely, then you're just a miss the donkey entirely kind of person. The fact that you had the number of spins that you did doesn't matter. Doesn't influence it whatsoever. So getting what I got by luck, right? Any regression line that I ended up with, anything that looked like a linear pattern of any kind, was that you just happened to be assigned the number of spins that you did when you got the distance that you were destined, predestined, fated to get. So if I want to simulate the null hypothesis, then I'm going to scramble those up, right? It could have gone another way, right? You could have been randomly assigned a different number of spins. So I'll look at that. I'll take all of the x values from the points in my scatter plot, and I'll mix them all up, and I'll get totally new points from it. And I'll do that 10,000 times. 10,000 times, I'll get 10,000 new scatter plots of the points that I would have gotten if you had just happened to be randomly assigned a different number of spins. And that's the way it's going to work for any regression here. Any time I'm looking at correlation between two variables. To get what I got by luck would mean that the response variable was going to happen either way. It just happened to have the particular explanatory variable that it did. So I'll mix up all the explanatory variables and see what could have happened if it had had something else. So how do we simulate the null hypothesis? I'll scramble around all of the x coordinates of my points. You could also say that you'll scramble around all the y values of your points. It really doesn't make a difference. What value should I be paying attention to when I simulate? I'm going to be scrambling up my x values 10,000 times. I'm going to get 10,000 different scatter plots with 10,000 different regression lines for them. What value should I be looking at 10,000 times to compare to when I did it in my experiment? We've actually got three different options here. One of the most common, and arguably one of the best options for us, is to look at the slope of the regression line. I get 10,000 regression lines. How many of those 10,000 regression lines have a slope that's at least as big as the slope that I got? Another option would be to use the correlation coefficient r. And similarly, you could use the coefficient of determination, r squared. Any of those would serve as a perfectly fine statistic. when it comes to simulating our null hypothesis and paying attention to something 10,000 times. Whatever it is that we pick, we just want to see how many of those 10,000 times was that statistic as extreme as it was when we did it. Now, if I'm doing a simulation, I'm going to go for that first option, the slope of the regression line. Let's see what that looks like in the applet. I've copied my data from the PowerPoint table after my macro collected the data, and I'm going to copy this from Excel, and I'm going to paste it into my applet. The applet I'm going to use here is the correlation regression applet under the quantitative response heading, since my response variable is indeed quantitative, as is the explanatory variable. I'm going to clear the data that they have here, and I'm going to paste mine in. I'm going to make sure I don't have any blank lines here at the bottom, because that's messed things up in the past. And I'm going to add some headings up here, because it really relies on those. So I've got spins, space, accuracy, and I will use the data. There's a lot of really interesting options here. You can see the descriptive statistics that will give you the mean and standard deviations for each of your quantitative variables, both the explanatory and the response. There's some neat kind of exploration options here where you can try to guess the regression line if you check this, and then you can tilt it up using this and move this up and down. It'll give you the equation here, and you can check this box to see what the residuals look like, so you can try to minimize them, or even the squared residuals, since that's really what you're trying to minimize and make it as small as it can be. It's a fun game. It's a great pastime, get your buddies together and see who can get the most accurate one. Or if you're a no-nonsense kind of person, you can just check this line over here to see what the actual regression line is. This up here, by the way, is another kind of exploration thing that really lets you kind of look at influential observations and what they can do. So you can click on points and remove them from the data, or you can add points to the data and see what effect that has on things. But I'm a no-nonsense kind of person, so I'm going to check this line that says show regression line. And this is going to give me the equation for the regression line. Again, I'm using my data from my section 6 class that meets at 2 o'clock, and it's going to give me the equation of the regression line just like we found in class, with that y-intercept of 112.43 and the slope of 18.19. I like the way that they write it too. They write accuracy and they try to put a little hat over it as best they can, and then they say 18.19 times spins, the explanatory variable. Here, if you want, you can see the residuals and the squared residuals, see it the best that it can be. You can also see some of these other statistics, like our correlation coefficient, which we found to be about 0.419, or the R squared, which we found again to be about 0.176. But when it comes to actually getting the inference, it's time to show shuffle options. I'm a 10,000 kind of guy. Ooh, my browser even remembers. Oh, it knows me. And here, apparently, the applet likes to think about it as shuffling Y values instead of X values. You know what, hey, everybody has the right to say it how they want. So I'm going to shuffle those Y values 10,000 times. 10,000 times, it's going to give me a new scatter plot with a new regression line. And I totally forgot to pick a statistic, and it's very kind to just pick one for me. Over here, I would have to choose slope, the correlation coefficient, the R squared. You could also use like the y-intercept and things like that, but slope is kind of what I'm going for. Here again, you can see your most recent shuffle. Here's the 10,000th scatter plot with its regression line, which I think the most recent regression line is actually this blue line here, which is mostly horizontal. And now I can do what we did before, right? I simulated the null hypothesis 10,000 times. I got 10,000 scatter plots with 10,000 regression lines, and I kept track of 10,000 slopes. How many times was the slope at least as extreme as it was for me? I'll go ahead and make it beyond. We'll call it a two-sided test. And be prepared for things to lag a little bit here, because having these 10,000 lines here actually takes a little bit of memory. Maybe it's time to reconsider being a 10,000 guy, but I don't want to. My browser just got to know me that way. So I'm going to go beyond the slope of my regression line. This is what we saw when we did it. This was our slope. And we're going to count the number of times that happened out of 10,000 times. Oh my word. It only happened 270 times. That means my p-value is 0.02. Do you know what this means? I have a significant result. It finally happened. I'm so happy. I actually have strong evidence of something. The number of spins actually affects your accuracy. This is the best day of my life. I mean, aside from, like, my wedding and the day that my daughter was born, it's probably third. I'm gonna celebrate with another milkshake. Section 4, when I do a simulation of 10,000 shuffles with your data and use your statistic, because the slope of your regression line was 37.25, I get a p-value of 0.1619, which is unfortunately weak evidence. I guess I'm not hugely surprised. I could make it a one-sided test and drop it down to 0.08, call it moderate, and make it a great day, but what's the point? Speaking of points, I would be interested in what would happen if I took away this outlier. Well, let's find out. I'm gonna click on this point and delete it. Out it goes. Now what's my regression line look like? Alright, not bad. Correlation coefficient of 0.44, that's way better. And R squared of 0.202, man, this is phenomenal. This has really got a chance. Taking away that one outlier might actually make this significant. I'll simulate it 10,000 times. Thanks, I appreciate you. Change that to beyond. Everything's gonna lag. My phone's gonna make a sound, but I'm not gonna let it ruin this take. Count it. What do we got? Out of 10,000 times. How many times does it get that big? I mean, this is kind of like right on the edge there. Look at that. 0.02. Haha. Significance once more. Which brings us to our last question. How can we do it without simulating? Is there a theoretical approach here? And here I've got phenomenal news. If you pick your statistic to be either the slope of the regression line or the correlation coefficient, then when you simulate the null hypothesis 10,000 times, get 10,000 scatter plots with 10,000 regression lines, if you keep track of 10,000 slopes, the data that you get will have a normal distribution. The good times are here again. Which means we get to go back to answering just our two classic questions, starting with, what are the validity conditions? I had to stretch out the clip art there to make everything fit on this slide. You can hardly tell. There's actually 3 validity conditions here. Number 1, points in the scatter plot should generally follow a linear pattern. When I look at the scatter plot, it shouldn't be total chaos, and it shouldn't be something non-linear. Second, there should be about the same number of points above the regression line as there are below. So no wildly influential observations that are dragging the line way above the data or way below the data. It should split it about in half vertically. And then finally, the points should be distributed fairly equally along the horizontal axis, the x-axis. No outliers in the explanatory variable. I want to avoid not only influential observations, but some of our math that's happening behind the scenes here is also relying on the fact that I don't have any major outliers, even if they do stay within the main pattern. As long as these 3 requirements are met, I can take a theoretical approach. Otherwise, it's simulation for this guy. Our second question is, what is the standard error? And here I have sad news, because the standard error actually is a pretty complicated formula, so we're not going to talk about it here. Instead, I'm going to rely on technology to give me that value instead. In the applet, I can get all of my theoretical results by checking this box here for regression table. Here it's going to give me all of the information that I'm looking for. I'm only really interested in this line in my second row, the one that's talking about the correlation between my explanatory variable spins and my response variable accuracy. And so here it's giving me the slope here of 18.19 like we had a moment ago. Here it's giving me that standard error. This is the one that I am not showing you the nasty formula for, but this is where I would get it. I would get it right from here, 7.723, and it'll give me my theoretical t-statistic, 2.36, that's bigger than 2, so that is strong evidence, and it's giving me my theoretical p-value of 0.0263, all confirming what we saw in our simulation, that I should reject the null hypothesis, that there is no association between these two variables, and accept the, well, not accept, but, lean towards the alternate hypothesis that there is an association. I could also get a 95% confidence interval for what the slope is. And here that is pretty wildly unhelpful. Here we've got, remember the slope that we had was 18.19. That's the slope of our regression line here, right? What is the actual slope in real life for the whole population, not just our sample? Well, we're 95% sure it's somewhere between about 2.32 and 34.07. Which is a pretty dramatic range, but nevertheless, here we are. Main focus is on my t-statistic and my p-value. And again, this is the standard error for the b value, the slope of my regression line. Section 4, your t-statistic was 2.41. Again, strong evidence, and supported by this p-value that's less than 0.05. With a 95% confidence interval of the slope, somewhere between 3.91 and 51.05. Unless, of course, you bring that outlier back into it. Now the p-value is way back up to 0.15, which is actually less than it was with simulation, and my t-statistic is down to 1.45. Not even moderate evidence, no, so bummer there. It's worth noting that I could calculate the t-statistic by hand as long as I'm provided that information from the applet. I'm essentially saying that my t-statistic is the value b of the slope of my regression line minus 0, the slope that the null hypothesis says that the regression line should have, divided by the standard error of that value of b. Well, b I've got from my regression line, 18.19, and from that chart on the applet, that regression chart, I know the standard error of b to be 7.71. So I could calculate my t-value of 2.36 by hand, but I have to be told that standard error since we don't have the formula for it. So, for our conclusions, finally, at long last, when it comes to significance, I actually have strong evidence. My p is less than 0.05. Oh, it's been too long. But I do have strong evidence, and I will reject the null hypothesis that there is no association between the two variables. As far as estimation goes, well, we saw the 95% confidence interval for the slope of my regression line being between 2.32 and 34.07. As far as generalization goes, well, that's a sad tale as always. I can't generalize beyond my sample because I did not have a random sample of all people who are under 25 years old. In causation, well, now that I have a significant result, I can actually say that there's causation. I had random assignment. I randomly assigned your value of the explanatory variable. Yeah, it was quantitative, but I picked it at random. So I can feel confident that that actually is the cause. That if you did pretty well, it was because you had fewer spins, and that people who had more spins, that's actually the cause of what led them to be a little bit farther away. I always enjoy this part of the process, and I'm sad that we can't have it in person, but I'd love to hear about what thoughts you have about what could have gone differently in this, things that may have impacted the data, things that it might make you think about trying for another time. And one thing that I was thinking about was maybe trying to find a way to have more consistency between the ways that people are spun. Like if I had you sit down in a spinny chair and I spun you around, but then you'd have to stand up and get, I don't know. It's worth thinking about though. Well, hopefully this has been informative and helpful, and I really hope that it makes sense. If you have any questions about it, feel free to reach out to me. I'd be happy to answer any clarifying questions or elaborate on anything, or even go through some more examples. Thanks so much for taking the time to watch this. I appreciate you, and I will see you later. Take care.